Hey, what's up guys? Baby Bear 4812 coming at you once again. Today we're going to be solving a relatively popular problem called jump game. It's problem number 55 on Leetcode. And it's popular with good reason. Overall, it's a pretty relatively easy problem to understand, although to solve in the most efficient way is not necessarily obvious. So let's take a look at the problem first before we walk through a solution. The problem states, given an array of non-negative integers, were initially positioned at the first index of the array. Each element of the array represents the maximum jump length at that position, and we need to determine if we can reach the end of the array, or this final index. To walk through a quick example, we've got an array 2, 3, 1, 1, 4, each step telling us how far we can jump. So from here, we can either jump one step or we can jump two steps up to this index here. Excuse me. From there, we basically need to ask ourselves, is it possible or not to make it to the end of the array? In this case, it is. We can jump from index 0 to index 2, index 2 to index 3, and then to the end. Once we reach the end, everybody's happy. In this case, it would fail with this array 3, 2, 1, 0, and 4. No matter where we jump from, we would actually always land on the 0, from which point we cannot make it to the end of the array. So, should make sense. The follow-up to this problem is a jump game 2 problem, which I will solve as well. I'll leave a link in the description below, which is definitely a trickier problem, but this one I think we can handle. Now, just to kind of talk about, general approaches here, where our mind might go in terms of how we would logically approach this. We could think to ourselves where, well, let me kind of take this first step and jump as far as I can and take a greedy approach. If we think about something like a greedy approach, that may work in some cases, but not necessarily in all of them. And let me give you a quick example. I can just select a pen here. Let's say that I had an example, and I'll give a very, very kind of simplistic example here. My pad isn't working. I'll give you a very simplistic example where let's say we had something like, we had 2, 3, 0, 0, 1. If I took a greedy approach, that is excessive. I'm sorry, there we go. If we took a greedy approach and said, okay, well, I'll start with this 2 and jump as far as I can, well, we're going to realize we get stuck in the bed with nowhere to go really quickly. So it's one example that disproves greedy approach not working. Another one which you might be thinking about, which is a valid solution, would include backtracking. Now, backtracking would, on a high level, I'm not going to go through the solution since it is an exponential solution. It'll essentially say, try every possibility. If you get stuck, backtrack to a point where it did work or you were in a favorable position, and then try again with another combination. There are many problems out there, which we'll talk about. I think I'll have a Sudoku solver as well. I'll leave that one in the description too. That one is a great backtracking problem. Here, not really necessary. The approach that we want to take here is going to be as follows, and it's not, I'd argue that it's not necessarily an intuitive approach. Let's work it through with this example here, 2, 3, 1, 1, and 4. I'm going to draw this on, say 2, 3, 1, 1, 4. And as always, if you haven't tried this yet, I would suggest pausing the video here, giving it a shot yourself, and then coming back to see how we actually solve it. What's not intuitive about this is the problem says we start right over here and we want to find a way, to get to the end. Naturally, that kind of tells our brains, well, let's start looking at the beginning and then see what kind of jumps we got to make to the end. However, somewhat potentially counterintuitively, we actually want to solve this by looking at the end of the array first and working our way backwards toward the beginning. So we'll start with the end in mind and then work back. Now, let's think about how that'll work for a second. Let's entertain one thought here for a moment. Let's pretend that all I had was this one step 4 here, or maybe I'll just say this was my array. It was this one element 4. By default, we win. Like, that's it. We're already at that final element. We're all good to go. Fine. Then we take let's pretend we said, okay, well, what if we had these final two elements together? We had the 1 and the 4, and then we can ask ourselves, okay, well, from this 1 over here, can I make it to the end? The answer is yes, I've, just enough leeway to make that one jump. Then we go over here, and we ask ourselves, well, okay, well, what if could we do it from here? Well, we said that from here it was true that I could make it. We also said that at this point it's also true. So then surely, just by logical extension, if I can make it from here to here, then I win. Because that I know from here, I can definitely make it toward the end. And that's the logic that we're gonna pursue here. Same thing over here. If I can tell myself that, if I can make it to any point in the array that I know I can get to the end from, then I win. If I can find a point in the array that I can say, if I was to reach this point from where I am, I can definitely make it toward the end, that's game over, and we return true. I think it's true that we got to return. Yes, we return true. So I hope that makes sense. As per usual, drop a question down below if it doesn't, but maybe once we get into the code, it'll be a bit more clear. And I do think we're in a position now to dive into the code. So let's take a look at this approach and see where it gets us. So first thing we want to do, as per usual, is to do our standard error checking. What we'll say is that if we're given some empty array, then we are going to return false. Apart from that, I think we're pretty much in the clear. Now, what do we want to do here? Well, I kind of mentioned this approach of keeping track of which parts of the array we can make it to the end from. So for instance, imagine I had something like, imagine this was a 0. I would kind of say, sure, I can definitely make it to the end from here, but I definitely can't do it from here because if I can only jump 0 places, that's not enough to get me to a place to which I can reach the end from, or to the end itself. So that's not going to work. We look at the 1, the maximum kind of length of the 1, it won't get me anywhere that I can actually get to the end from, so that's not going to work. But, this 3 is sure as hell works because I can take a, 1, 2, 3 jumps over, and I can land on a position that leaves me saying, yes, we've made it to the end, or yes, we can make it to the end from here. With this logic in mind, it might be tempting to say, let's just create an array of length n and plop in a bunch of Boolean, trues and falses and say, yes, I can make it to the end from here, or no, I cannot make it to the end from here. However, we could do it in a slightly more efficient way, which we're going to do, which is just going to be to keep track of the last index from which we could make it to the end. If we continue that pattern and the last index from which we can make it to the end is 0, namely this one right over here, then we return true at the end of the day. I'm going to repeat that one more time just to be clear. If we get to the end and we say the last possible index that can definitely get me toward the end is the index 0, or our starting point, then we return true. That's going to be the logic on how we're going to optimize this problem here. What that'll do actually is that'll give us a straight linear time complexity, and in terms of space, it'll actually give us a constant space complexity, because all we need to do is really store one variable. So that's the key to really optimizing this thing here. Now, where were we? What we can say then is to say maybe the, I'll call it the last possible index, just to be super creative. As of right now, we know that the last possible index from which we can make it toward the end is the end itself. So I'll say that's going to be length of nums minus 1. Now, what we want to do is walk through the rest of the array backwards this time to see if I was to take one more step back, can I still make it to that index that I want to make it to? So we'll do that here. So we'll do a wicked cool for loop. And then at the end of this, I know that we're going to want to return essentially this. We're going to want to say if last possible index is equal to 0, return true. Otherwise, return false. What I'll do is just to keep the code a bit more succinct, we can simply just say, let's return last possible, possible index equals 0. If the statement is true, we return true. If it's false, we return false. So that kind of keeps it in a nice one-liner. Now, we want to loop backwards from the second last element toward the beginning, like we were saying. So we'll say for I in range from the length of the array -2, and we want to make it all the way to the beginning. What we're going to want to do is this, is we're going to want to check the height, or excuse me, not the height, mixing that up with another problem, the maximum number of jumps we can take from our initial position to see whether or not anywhere in that distance we can potentially land on that last possible index. So what we'll ask ourselves is, if nums of I is greater than or equal to last possible index minus I, then we want to set the last possible index to equal I. Now, I want to make this point clear because this is kind of where, this is the bread and butter of it. Last possible index minus I is the difference between where we are now, and where we would like to be. If I can jump at least that much or more, then that definitely means I can land on this last possible index, which is guaranteed to take me toward the end. As long as I land on a position that's guaranteed to take me toward the end, I win, I'm happy, I get that job at Google, we celebrate. So, with that said, I actually think that this is just enough code to get us to where we want to be. It's a pretty short solution. Now, before I jinx it, let me run this super quickly and make sure that I didn't do a silly, and I did not do a silly. There we go. So that was a relatively quick, I'd say about 10-minute solution. It was in linear time, constant space. It's the optimal way to solve this problem. The follow-up is harder. As you can see, there's a jump game 2 and 3. I'll have those uploaded, linked in the description. Check these out, give this one a shot yourself, and as always, if you didn't really come to this solution intuitively on your own, don't beat yourself up about it. I kind of say this over and over again, but part of the challenge and part of the exercise in going through these problems is to learn new ways of thinking. These new ways of thinking aren't necessarily always intuitive. They're incredibly intelligent minds who worked on algorithms and problems for decades and centuries before us. All we can do is learn from them, pick up new ways of solving problems, and then as we go on and learn how to solve these problems and new methods, we've now developed tools that exist in our toolkit to tackle stuff like this. So, thank you for coming to my TED Talk. That was the solution. If you found it useful, leave a like, subscribe. Any questions you have, any questions you want me to answer, leave them in the comments below. And I'll see you guys next time. Peace.